All right. All right, guys, how's it going? Big Mike here with the Engineers for Communities live show. We have a fantastic panel today from Powell Water. Um, just to do a quick introduction, we've got Scott Powell, Judd Sundine, and Jeff Couch, and they all work different parts of the puzzle here. I think Scott's going to start us off and kind of explain who and the how behind your group.
Yes, we do actually Powell Water Microalgae Systems, which is the combination of our three expertise. We start out with lagoons. We place microalgae in lagoons, which use photosynthesis to put oxygen in the lagoon. It'll save you 90% of the electrical cost of the typical blowers. We follow the lagoon treatment with electrocoagulation, which will polish it, take out the bacteria and virus and the BOD, TSS, FOG, phosphates,
Okay.
heavy metals that are left.
So take me back a little bit. Just wind me back the clock. How did you guys get started, and what was like kind of the mission and the goal that you guys are come with this amazing product or just system?
We're very environmentally conscious. We feel that it is a sin to pollute water in the name of cleaning it. And so instead of adding chemicals into the treatment system, which is typically a salt that part of it does some good in the treatment and the other is just a pollution for the water, we use natural things. In this case, we bring in the sewage water, and of course it has the food in it that's left over from the people who digested the product. And we place it in lagoons, which is basically a wide spot in the line. And we add microalgae and some microbes designed to specifically make oxygen from sunlight. So it takes the carbon dioxide, converts it to oxygen so that we have a great biological process for consuming those products. And then we polish it. Judd is our expert on microalgae and microbes. Judd, you want to tell them how that works for you?
Sure, I'll take the microalgae, and I'll let Jeff do the microbes. The microalgae, we pick certain, species depending on where the process is located. We use typically 2 to 3 different kinds of microalgae, and we grow them in a greenhouse in tanks, and we infuse that microalgae into the lagoon system in various portions in various spots. And so it creates 100% oxygen as opposed to the 21% oxygen that the blowers typically use. So that's how we get the microalgae in to create 100% oxygen. That's the short answer. And I'll let Jeff go on the microbes.
Yeah, I'm kind of a small town guy and got involved with small town, typically towns less than 5,000. And so as I visited facilities around the Midwest, especially Oklahoma, Missouri, Arkansas, all over, you walk into those facilities and the first thing you see are all their blowers are on it's not only the cost, but the blowers are broken down and sitting on the side of the lagoons, not working. And so I figured there's got to be a better way. So we kind of got into the algae. And then the other thing the operators always said is they don't like the UV lights and they don't like the basically the chlorine handling the canisters and stuff like that. And so Scott's EC worked out perfect for the disinfection at the tail end for tertiary treatment. And so we put those together. And like I said, we've been working together for 15 years now to do this. And we've got some plants in operation. It's worked out very well. So the algae will keep the lagoons up to, we can keep 20 milligrams per liter of oxygen in those lagoons, pure O2 molecule. And when you've got that much oxygen in a lagoon, magical things happen.
So I got a quick question. In the lagoons, I guess just try to understand these lagoons, your customers you're working with, are they historically cheaper? Were they quicker? Are they like, when were these things installed that you were running across when you were kind of going through all these communities?
Sure. Basically, most of those lagoons went in the late 60s, 70s, and early 80s because they were economical to do. You dig a hole in the ground and put some sewage in it, and it worked. What's happening now is that basically the regulatory people, the DEQs and whatnot, are starting to ratchet down on the limits that you can discharge into receiving water's body. And the lagoons work great up to a point, but they can't bring ammonia down to where the regulators want them. They can't bring the phosphorus down. The disinfection standards have gone up. So this worked out really well, and we can basically encourage those lagoons to work a lot better. Recently, we run into some more significant reductions in limits for discharge. And so we started adding microbes, and we've been able to custom those microbes for the sewage. We pull samples, we test in a lab, and we design these strains of microbes specifically for that lagoon. And it's been very successful. And we can almost eliminate ammonia, almost eliminate phosphorus, and set it up so when the electrocoagulation gets the water at the tail end, it's like a finishing or a polishing unit, and it takes out everything else. And we can almost mimic a mechanical plant for about a quarter of the cost.
So I had another engineer ask me specifically about the microbes. They were asking me, how do you stop them from continuing forward in the treatment process and just keeping them in those first steps?
That's pretty simple. Microbes and microalgae only grow when there's food to eat. So if you have long enough time in the lagoons at the start, there's a lot of food, and as it goes through, they get hungrier and hungrier, and they starve to death before they get to the end. And if they haven't died by the end, we shock them with electricity and put them out of their starving misery.
When they die, do they fall to the bottom or do they dissolve into the water?
They're cannibals. They eat themselves until they're virtually all gone.
Gotcha. Okay, so the first step was, I'm just trying to summarize kind of I guess my next thing is, how do you keep these alive, or what is like an operator, how do they work with the microalgae?
So Judd has a greenhouse and he incubates them. And basically he's got the strains that he wants. Each one has their own container. He feeds them and takes care of them in a great environment, and then he puts them out into the lagoons continuously to thrive and grow in nature. So they're continuously fed, continuously grown in the greenhouse.
Does and I'm just asking lots of questions because I feel like this is something in a rural community. It's like it could be a really powerful tool. This whole treatment train you guys are working with. What is the footprint compared to some of the other treatment plants in terms of square footage overall?
Well, of course, lagoons take up space, and so in a rural community, that's great because most of the time they're surrounded by farmland. It really works well if those existing lagoons are there and they're kind of sludged up and they're kind of tired. We can eliminate all that sludge and basically supercharge them a little bit. Typically, I put curtains in and what I call racetracking the lagoon, so there's no short circuiting, so the algae has time to mingle with the solids that come in, the organic material. Give them plenty of time. We need 18 days roughly in the lagoons. And so we typically have that facility there, but if you're talking about a town of 1,000, you probably need about 4 acres. If you do an SBR, an MBR, a mechanical system, you probably need an acre. So I always say I can sewer New York City, but I need Delaware to do it. So, last time I checked, Delaware wasn't for sale, but so lagoons need a little bit of space.
That might be one of the best phrases I've ever heard in engineering. You're saying you could treat all the water for the people in New York, but it's going to take a whole nother small state to in lagoon area and treatment facility size.
The people from Delaware say, no, take New Jersey, but that's another whole discussion.
Oh, are you from up north?
No, I'm from South Dakota. We
Okay.
don't understand that at all in South Dakota.
Okay. So talking about that greenhouse, I'm completely naive to it. How do operators get educated? What kind of licensing, at least in Colorado, would you need to operate it? What does that look like from the end user getting up to speed?
Judd, you want to take that one?
Well, it's very simple. You just make sure the food is there for the microalgae and the microbes, and they pretty much take care of themselves. In fact, we've had operators. We also, just an aside, we put in koi in each of those tanks, and they're kind of the canary in the mine shaft. If something happens to those koi, we know that there's something wrong with the system. And so we've had operators really name the koi. They've actually gone fishing in there, and it's kind of a greenhouse, has so much oxygen in it. You don't have to pay to get an oxygen treatment. Now they can just go in there, and they've spent a lot of time in there actually. So the maintenance on it is nil. It's virtually nothing. You just have to check on it every now and then and do DO readings, and that's pretty much it.
So you're saying instead of these hipsters going to the oxygen bars downtown, they should come to your greenhouse?
Absolutely. Absolutely.
Actually, we can run the tanks up to about 40 milligrams per liter. And in a hot summer day, you walk in and it's like literally walking into a hookah bar. And so our problem with the greenhouse is that the operators won't leave. They like to stay in there. So anyhow, it's quite a deal.
Back to the difficulty of growing the microbes. You might think of how hard it is to raise bread with yeast or to make beer. I mean, those are growing these little creatures and making a product. So it's not complicated. We do it all the time or see it around us in our life. We just haven't focused it in this area. It's not difficult.
So, well, man, I kind of blanked. That's what my next question was, is what is it just look like a standard greenhouse? If I'm driving by, am I gonna like be staring at this thing? Is it, kind of, there's a pond in it with koi in it? Like, tell me more.
The greenhouse is 16 foot wide by 107 foot long. You can buy them at any industrial shop anywhere. It's a standard, typical greenhouse you see in a nursery. We do reinforce them a little bit so they'll withstand 100-mile-an-hour side loading, 130-mile-an-hour gusts, because we do get those in Colorado. But it's a stout little thing. But there's 8 1,000-gallon tanks in there, and we put water in the tanks, and then we take water off of those tanks, the same amount, and run it through a manifold and inject it out into the lagoon. And typically for 140,000 gallons a day, we'll run 6 lines out into the lagoon. And we'll basically the algae will be distributed through those lines. So
the water in those tanks, is it just reuse water coming from the effluent?
Right now we start with typically potable water. Typically the lagoons are at the end of the town, so the chlorine's already gone out of the water, and basically go start there. We add a component as we get going and we clean things up. Then we can reuse water basically from the EC. We can recirculate it and bring that water into the tanks. And so we can basically have a closed system there.
How do you guys deal with the rough, harsh temperatures in Colorado? I know that some people will say, well, the lagoons are great, but the water gets so cold, like the nitrogen, and that's some of the issues, and they kind of like write these off. How does it fare? How does
Judd has actually found microalgae from Rocky Mountain National Park that grows underneath the ice. So that's a fairly harsh environment. So he actually locates these microalgae, the ones that he starts with, and continuously feeds, and they grow independently in this greenhouse. And then when they get to the lagoon, they've got to rough it for themselves, and they have to live in the environment that's there. So the ones that like to live in the cold water, they survive, and the others go dormant. And the ones that like to live in warm water, they work well in the summer and morning to night, winter to fall.
Okay, so that was really interesting. I had no idea that there was microalgae growing up in Emerald Lake and up in Rocky Mountain National Park. I just assumed it was a barren place.
Oh, no, not at all.
Yeah, we do the same thing with the microbes as well. The microbes slow down a little bit, but we continually introduce those as well, and they slow down. We have 3 projects now at 8,000 feet above sea level. Ice comes in about end of December. It'll stay there till March. And basically, the testing we've done so far shows that they continue to function very well.
So is it kind of similar to like engineering plants? Like we'll talk about Monsanto or something like that, how they take the crops and they kind of evolve it over time to make it exactly what they need to work in that field with that kind of, soil moisture content and micronutrient availability. Is that how these are selected?
Well, they're doing gene splicing. Judd just goes out and finds already living organisms that meet an environment. So he selects an organism for an environment. I mean, let's be honest. Those companies you just mentioned, they're splicing their plant so they can put Roundup on it, and their plant lives and everything else dies. Judd wants everything to flourish until they starve to death before they leave the lagoon.
Okay. Yeah, I wasn't trying to say we were going to throw more chemicals on it. I was just trying to say, okay, like there's a planning. It's a tried and true kind of method we've used for selecting things in agricultural, just human history.
Some people milk Hereford, some people milk goats, some people milk, horses. Just depends on what you want to get your milk. Judd selects the one that meets the environment that works.
Okay. I think I've got it. Okay, so that's the first step. Now, do you guys do the other parts of the treatment train as well, or are you guys mostly in the lagoons and in the electrocoagulation? Is there a secondary treatment that usually accompanies this?
Well, so it depends on what your process is. If we're in a place that has, say, high sodium chloride in the water, then after the electrocoagulation process, we might put in reverse osmosis so that we can put fresh water in a stream and concentrate the sodium chloride to go to an evaporation pond or something of that nature. So we believe in giving the customer what he needs. If he only needs one component, we're happy to sell him one component. And if he wants a system so he has one gelable person to send a gel if it doesn't work, we're happy to give him a complete system, whatever they like.
I'm sorry, did you say send to jail?
Yeah, the EPA has what's known as a gelable corporate officer. If you cheat on your discharge permit, somebody goes to jail. It's usually the gelable corporate officer that does that.
Okay, I didn't know that. I learned something new today.
In a small town, that would be the mayor or maybe a council member.
They go to jail if the effluent at the wastewater treatment plants been lied on, even though they know nothing about it.
Yep, they sign the reports every month, and they send those into the state regulatory people. And so I don't know of anybody that's gone to jail yet, but they have been threatened a couple times.
Wow.
Yeah, it's serious.
Okay. There is a reason we have publicly owned treatment works instead of just running raw sewage into the river. And that reason isn't because there's no enforcement or no penalty if you choose not to do it.
But Michael, back to your lagoon question. We have the greenhouse and we incubate the algae, but the first pond is a primary cell, does all the heavy lifting, takes out most of the solids. The second is kind of a calming cell, secondary treatment, and then we hit it with Scott CC, and that's the tertiary treatment. So it's a pretty simple footprint and pretty efficient, actually, and very effective.
So I want to learn more about the electrocoagulation because it's a very naive word to most people. I would think if as David told me, he ran across it and he's like, this is witchcraft. This is a witchcraft word. And he said coincidentally someone called him up the same week and was like, you should check this out. It was like a coincidence of fate. Can you kind of explain to me the process, the operator's part in it?
So I would be happy to. So Dave, representing, Round Mountain Water, and in his town, there's a person used to teach at Red Rocks Community College, Yarrow. And Red Rocks Community College is the leading water treatment operator school in the state, second in the nation. And they actually have a little electrocoagulation unit there. You can go and you can see it. Basically, it's just metal plates parallel. They don't necessarily, anyway, you put electrons through water and a metal plate. That's electrocoagulation. And where that surface of the electron and the water meet, you have a reaction. And for example, it will take arsenic ion that stays in the water. It's got a charge, so it'll stay in the water like a magnet on your fridge forever. When you put that charge through it there at the metal plate, it will turn it into a oxide form, which is like a rock, and then it'll settle out. And so you actually convert that hazardous waste back to its original form in the ore that it was mined from. So that's the basic process of electrocoagulation.
Okay, so how long do a set of plates last?
Typically, they dissolve at about 0.2 pounds per 1,000 gallons treated. You put in as much electricity as you want to dissolve the plates, so you can dose it like you would chemically. 0.2 pounds of iron is about 25 parts per million of ferrous sulfate. And so
in one of the sites, like in Oklahoma, they replace the blades every 6 months, and that's for permitted flow of 100,000 gallons per day. The trick is not to have to replace them all at once. You go every week and check them, and then some will wear quicker than others. So you take them out a little at a time. Every week you go through and take out a few and put in a few new ones. So it's kind of a continuous thing, but average, if you just leave them about 6 months. If you're running hydrocarbons out in the oil fields, they probably go a little quicker and than that. If there's more burden in it. So it varies depending on what you're running through the system.
So go ahead, Scott.
So it's sort of like a thermostat on your wall. If you need more stuff taken out, you just turn up the electricity going through, and if you need less, you turn it down. It's current controlled, so it basically measures the ions in the water, because that's what conducts the water through the electricity through the water is the ion. So if there's more there, more electricity flows through. If there's less there, it doesn't have the conductivity and doesn't draw the electron through the water.
So when it reacts with the metal in the water, it creates a new solid that dissolves out. How many pounds per week are we talking at like 100,000 gallons a day?
So that is an excellent question. The United States EPA says electric coagulation as compared to alum coagulation, chemical, you have 83% less solids, and it filters 76% faster. So you have 83% less solids with electrocoagulation versus chemical coagulation. And the primary reason for that is chemical coagulation makes a hydroxide flock that holds water, whereas electrocoagulation makes an oxide flock that doesn't have a charge on it, so it doesn't hold water. Therefore, the water passes through it.
Oh, that's really interesting. So you're actually putting more of the water just straight back in the what dissolves out is not as wet, or I don't know. Maybe I'm not.
It dries. It dries faster because it is in an oxide form. For example, people can relate to a diaper that you put on a child, and this diaper is there, and it's got some polymers in it. And when the water comes in, the polymer absorbs the water and takes it away from the child. Then you take that diaper, now that's got the polymer in, it's wet. If you were to set it in the corner, it would stay wet for 6 months because it holds the water. That's what it's designed to.
Gotcha.
With electrocoagulation, you coagulate it, you filter it out, and you can literally watch it dry and crack in a few hours. So it repels water.
Yeah, in a municipal application of a town of 1,000, basically, we run through the machine. It comes out of the machine and it's kind of a slurry. You can dip it with a cup, and the solids will settle, and the water comes to the top almost immediately. So you know exactly where you're at, how much electricity you need to add, or if you need more time in the chamber. When it comes through that, once you get that right, we get, in a town of 1,000, we get about 10 pounds a day of solids, 2 5-gallon buckets. And we run it out into a drying bed. It cracks immediately and dries up. And no equipment. They take a shovel and shovel it in a bucket. They actually put it in their dumpster, and it's gone. So that's because we've taken so much of the solid and the bad stuff out in the lagoons. We don't have that many solids left. And we have the PSSs are always below detect, and the BODs are typically all down. Through a lagoon, we get typically 2 to 3, less than that sometimes. All the biologics are gone, fecals, E. coli, they're gone. Below detect always. And so it kind of gives you an idea. Yeah, very efficient to run it, and they can do it with one guy. You asked about licensing, by the way, back there. If we don't have the EC on the end of it, sometimes we don't. We're just running lagoons. Basically, you can run it with a Class C license. Typically, that's not hard to get. If we add the EC, sometimes the states will want us to do a Class B operator. And of course, that you have to have a little more sophisticated guy. They have to have some time served before they get a license. So it's fairly simple along those lines as well.
I feel like from what I've seen, that Class B is becoming more and more common just to meet, at least in Colorado. That's the minimum things that are going to be able to meet your requirements.
For a small town below 2,000, 3,000, they don't exist. And number one, and it's hard to afford them no matter what you put in. So we can kind of work that out through the lagoons. It's a little simpler. If you're running SBRs, MBRs, or oxidation dish or something, it's almost impossible to find someone to run those and keep them current and understand what's going on.
Gotcha.
Another meshing on your solids, you know how people put in methane digesters and basically to reduce the solids. But in the lagoons that we have, we leave it in there with a long enough time and enough oxygen that virtually all of the organics are consumed in that lagoon. And so the only thing left that's coming through, is you call it the ash or the mineral. So
we're actually an operator in a system in Oklahoma. We've been in line for 8 years. We have no sludge in the lagoons at all. And except for maybe in the corner, you might get a little viscous material in the corners as it goes around the curtains and goes through the racetrack portion of it. But basically, we eliminate the solids.
So it saves that problem.
So how big is because it sounded like in some situations you're just adding an EC onto the end of a treatment train. How big is the unit that houses it if they were just to add that?
For a town of 1,000 people, using say 50 gallons a minute system, it's a 30 by 30 building. Inside it has the EC. Typically we use a slanted plate clarifier like a lamella to separate the solids. The operator goes out once every 2 days and washes the solids out into a drying basin, what little there are. And then basically we have a compressor in there and some material for a backwash. But other than that, it's pretty simple. We put a garage door in front, a man door on the side, and it's a metal building. We basically pretty simple to build, and basically we insulate it a little bit for the wintertime. But so it's very effective in allowing space for that EC to do what it needs to do.
What about from the operator side? Do you guys have any remote monitoring installations, do you guys plug into like a high tide or any kind of SCADA? Like, what's the PLC look like for this unit?
So typically it's an Allen Bradley PLC. And of course, they have a module that can connect to the internet. So if you have internet connection, you can do that. It's pretty simple. So I don't know if you need that, but
No,
yeah, you can do it.
Some places I feel like are just so remote out there, and we're talking about these Class B operators to operate this thing. If you can keep the operator time down and they're able to check it on their cell phone instead of drive 2 hours to the site, be there for an hour to check something and 2 hours back, and you're getting billed 5 hours opposed to one. I could see the cost savings.
Well,
Yeah,
absolutely.
you can have remote monitoring,
We
SCADA monitoring.
haven't done SCADA to date, but basically we've been asked to come back and retrofit for the SCADA. Some towns don't even have computers, so they don't know how to monitor. But from now on, everything we do will have SCADA.
Neat.
Many of our industrial applications are set up where the cable that programs the PLC can also take it to a monitoring room. I mean, it's not a difficult process.
So, talking about cost savings, I think you had briefly touched on it. What if you're coming in and wanting to, you're a rural community, so you've got plenty of agricultural additional land near this town that you're building. What is the just cost per cost on the installation side? What are we looking at for operating costs, each month? Like, how does it compare if someone came in with like a new Terra MBR?
So I think Jeff mentioned at the beginning that compared to a mechanical system, we're about 40% of the cost.
Yeah, I'll give you an
So
example.
it's considerable savings.
Round Mountain in Colorado, the engineers come in, did a great job, said we can remove it. A lot of it depends on what their permit allows them to discharge, and what size community, but said, oh yeah, we can do this for you. Take the metals out, take the phosphorus out. It'll only cost you 14.8 million for a town of 1,000 people. And for that much money, they could just give everybody $50,000 and say, close the town down, get a bulldozer and start over. So we're in on that one. Basically, actually, I think they couldn't get the arsenic out. We do a much better job with the arsenic with the electrocoagulation, and we're down around 4 million. So $4 to $14 million, that's the cost comparison. It's a difference between the board still living in the town and not getting shot, and a town still functioning properly and being able to pave the roads occasionally. Another small one, 100 miles to the south, town of 300 people, the cost was $25 million. And there again, you could have bought the town. And so we're coming in for $500,000 and fixing, and we can do a piece at a time. And help.
Did you say 25 million to half of a million, which would be like, I don't know, I'm not a math wizard, but 50x?
Yep. And we have another town about 100 miles southeast of them, and they're having problems with their lagoons, and their discharge limits have been restricted a little bit more. And that estimate was 40 to 50 million for a town of 3,000 people. And so we're working on that one a little bit. I don't have our answer yet, but so basically that's the issue, that they're to deal with what the regulatory people and what they want to see in that water. They're imposing anywhere from literally from 30 to 50 million dollars worth of cost on these smaller communities. And so
do the permitting agencies have anything against lagoons, or like what like when you go talk to them, how like is there a wall that they put up, or how come more people are...
It takes me 2 years when I go into a state to kind of do the thing, because in defense of the regulatory people, they see black boxes and new technology every day. And so their initial response is, oh yeah, show us or do something or give us information, and then kick you out the door. And so it takes a while. And we're going through that process right now with Colorado. They ask great questions. They want to know every moving part, every piece of water. What are we putting in if we put anything in? And I respect that, because we can meet that. Almost everything that they throw at us, we can do with lagoons. Lagoons have been, kind of rough treatment, basically in the past. Regulated to small towns, we have 3080 regulations. They're not ratcheted down too much, but now they're starting to treat them like a mechanical plant, and they want those limits. They want arsenic at 0.02 parts per billion. They want phosphorus at 0.05 parts per million. In Missouri, they're dropping the ammonia down to 0.6, and lagoons historically can't do that. And so we're able to use that. The point is, we want to use that infrastructure and be able to supercharge it or add a few little things to it, and then make that system work like it should have worked in the first place.
And the state of Colorado has been very good with us. They've actually had some people that have come to Red Rocks Community College and watched for months at a time. Gordon Whitaker, and they've been good, and they've gone to see the commercial facilities that are here in the state that have operated for a prolonged period of time. So they're working through the system. And we're pleased with what they're doing. So on the other side of the capital cost is the operating cost. And with these nice, beautiful mechanical plants, you probably need 4 of those Class B operators. And with the lagoons, you need 1. And so there's quite a bit of savings in labor. The electrical costs saved by using the microalgae to say the electricity from the blowers will offset the cost of the electrocoagulation process to give them their tertiary treatment. So the operating cost is less and the capital cost is less.
Are you saying that the well, let's say you have an existing lagoon with blowers and you come in, you put the microalgae in, and then you put the EC unit on the back end. Are you saying that that's like a net zero electrical requirement demand on the facility?
Probably a little better than net zero, but yes, that's what I'm saying.
Absolutely. So
okay.
in Round Mountain's case, their operational budget was just for the wastewater was estimated to be $500,000 per year. That was the entire wastewater town budget for the whole thing. And so obviously they can't do that. So in one situation, we were able to take a community, 1,000 people, and we got it down to a point where instead of going through all of the resource funds or trying to do USD or rural, whatever, we marched them down to the bank and said, hey, can we borrow this much money? Yep, here's your check, and go build it. And so we can simplify the funding process in some situations, not always, but so it simplifies the whole thing.
One of the things I thought was interesting today was I was talking with people that work in the energy department, work with the energy department for the state of Colorado. So are you guys able to use some of these statistics to help get in front of those groups to say, hey, like we're solving 2 things. We're helping reduce the electrical demand, which is one of their things. And we are also working with the CDPHE to meet their requirements. Have you guys had any interesting encounters like that?
Yes, one of the buzzwords in our society today is greenhouse gases, mainly carbon dioxide. And the microalgae, of course, use photosynthesis to convert carbon dioxide to oxygen. So they're not sequestering it, they're actually using it, transforming it into another form. So this actually is reducing the carbon dioxide concern for greenhouse gases.
So just to put that in layman's speak, you've got you had blowers that need electricity that probably came from a coal, natural gas plant, something like that to produce it. That created a bunch of carbon emissions for those blowers to put oxygen into the water. Yep. And you're saying we're actually going the other direction. We're taking the CO2 that someone else produced somewhere else, and we're actually using it into our process. So it's almost you're flipping both sides. You're going both directions.
And it's well known, people say, hey, fly our airplane and we'll plant a tree to offset the carbon dioxide we're producing. In this case, the sewer plant is the microalgae. You consider just billions of trees. And so now the sewer plant is actually producing billions of these trees or microalgae that convert carbon dioxide to oxygen. At the same time, the microalgae bacteria in there, they need the oxygen to consume the food, to get rid of the BOD, and that will produce some carbon dioxide. It's right there for the microalgae to get, and so it's very symbiotic relationship. They get along real well. And the way Jeff's designed it, he's got his diffusers a little bit off the bottom of the lagoon so that he has an anoxic zone below that to get rid of the, the nitrogen, nitrates, ammonia. I mean, it's a nice little system that fits all together in that lagoon. And the good news is you don't have to go out in the morning to remember to turn on the sunlight, and you don't have to shut it off at night. So it's a marvelous system.
Another thing along those lines, the basic technology now is to capture carbon dioxide, put it in a pipeline, pump it to North Dakota, and pump it into a cavern underground. Well, what could go wrong? They leak, the pipeline doesn't work, costs $1 billion to do it. What I want to do is take flue gases out of simply always have cooling ponds in front, big ones. Take flue gases, run it through that pond, add algae in the pond, and we convert it right there. Don't have to pump it, don't have to do anything, it goes away. And so I'm working on that to see if I can't get a power plant to buy it to do a demonstration project. So I've been working on it a couple of years, but it is the solution for carbon capture in the future.
I had a really hard time following. I feel like you went so fast there. What power plant, or can you?
So when you burn coal, like you said,
okay,
part of that combustion process, if everything goes right, you make carbon dioxide. If it doesn't go right, you make carbon monoxide. It'll kill you. But when it does go right, you make carbon dioxide. And the carbon dioxide, of course, comes up in the atmosphere. And so the carbon dioxide can be captured up there and compressed and put in a pipeline and sent away. Or you could put it into the water, into a lagoon with some microalgae, and just convert it from carbon dioxide to oxygen on the same location and not have that pipeline. Is
gotcha.
That
okay.
help?
And that's what I thought. I thought he was saying, hey, we can treat it right here at the point source. We don't need to ship it away.
Yeah. Theoretically, it could be 0% discharge. You could take 100% out of the smokestack.
What so you said that these are some things you're trying to install at different power plants?
Yeah, some of the things we're working on to utilize the algae technology.
So that's really neat. So when people are saying is this at a natural gas, or what kind of plant is this?
Any place that burns has that process produces carbon dioxide, whether it's natural gas or coal or anything that burns. That's
okay.
That's how it works.
Gotcha. Wow, that's really neat. And then, so if the regulatory agencies, like the EPA, come back and say, okay, well, that you've got to offset your CO2 emissions. I don't know if they are or not. I'm not a air quality expert, but if they're coming back and saying, you guys have to do something about this, you're saying these ponds would be significantly bigger cost savings than them just paying someone or shipping it off away, which has a lot of potential to go wrong.
Exactly.
Well, and as you pointed out very well, the sewage coming from the town is there. It's a food source. And so instead of using this carbon dioxide producing electricity, you can actually use that as food to grow your microalgae and to convert the carbon dioxide to oxygen. And, you can do that at the town by the power plant, and everybody should be happy.
How big, if you've got a town of about 1,000 people and you had a power plant to support that? I'm just trying to kind of conceptualize this. That was one of my questions, was talking about going more towards these lagoons, the pond, the microalgae kind of systems, like a one system community. What kind of footprint do these ponds have for the power plants? Relative to the use that they demand for?
Well, you can look at any aerial photo in any power plant, and you'll see, along with the infrastructure of the power plant and the coal trains and all that stuff and access, there's always a big 40-acre lagoon or something like that next to it, or two of them. They have to use it for cooling of the flue gases. And so we might have to chill the flue gases a little bit, but we can run those directly and make use of those ponds for the carbon dioxide reduction. It's already all there.
Another thing that those ponds do is they collect the fly ash, those small particulate, and they bring them down. The electrocoagulation will drop all those small particulates out of the water. And
there's already a study done. MIT did a study, and they had achieved 97% reduction of carbon dioxide in their facilities in Massachusetts.
Wow, that's fantastic.
For a coal-fired facility.
What this was something I meant to ask is a lot of people complain that the lagoons smell. How do your lagoons smell? Like, is it any different?
We love that question. Thank you for asking it. Septic things stink. Septic means lack of oxygen. So when you use the microalgae and it's got 5 times the amount of oxygen in the water that these blowers can put in, you eliminate the smell. So there is no smell with the microalgae lagoons.
So when we take regulators through the system, one of the questions we always ask, did you notice that? And they all go, what do you mean, did I notice that? There's no odor. We walk around, and they go, it takes them a while, but they just go, what? We don't understand. What's going on here? And so it's pretty much odor-free.
Because, I went to, not to be disclosed, I recently went to a sewer plant that was built 50 years ago. And there's no, their headworks, it doesn't have there's no seal between that and the admin office.
Yep.
And it is disgusting. Your clothes, everything, they're ruined.
Yeah, I agree. We do get a little odor if the headworks are exposed, and naturally that's where the raw sewage comes in. You might get a little escape, but once we get in the system, it goes away. The methane, the ammonia, and the sulfur dioxide are gone.
Wow. All right. So my last kind of question is gearing towards that new community. The developer, he's got a choice here when he's building some new rural community, like let's say kind of like when Vegas was built, right? Like they're going out here, they're going to build, but not like with the intent of Vegas, but he's going to go out and build a new community kind of in the rural area where no one else is living. How do you guys see your system fitting into it?
We love that opportunity. So people like to shower and people like to wash their clothes. And that's about half of the water that's used, 2/3 of it. And then we like water to drink. And we would like to take all that water that goes down the sewer, put it into these decorative lagoons around the community. So you'd have grass-lined lagoons and the microalgae would be there. So there's no odor. You electrocoagulate that water, and then you take the water back to flush your toilets and wash your clothes, and it'll be potable water quality, other than it doesn't come from the best available source. Or you can just, make more golf courses or more parks or whatever with that water, and just use it within your community, as opposed to having to buy 100% of your water to come in.
Yeah, it's even better than that. When we're working on a community in Texas right now, and they want to treat, they don't have any wastewater facilities near them. So we're going to use the lagoons. The lagoons don't have to be square, ugly things. We're using them in the parks. We're using them in the golf courses, and we can treat right there and then use that water back in the parks and the golf courses. We use it for buffered open space. We use it for open space, and it's all lagoons. It's all part of the wastewater infrastructure, and no one ever knows, never smells, never a problem, and we get to reuse all of that water. It's the difference between being able to do a project on a 1,000-acre site and not being able to do a project.
Because of the cost savings from your plant, or
Well, you-
the layout, or is it both, or?
The whole thing, both things. You're going to have some open space, typically 10 to 20%. You're going to have a golf course or something on it, or a park. So you've got all sorts of grading and room for lagoons in there. And basically, if there's a buffer requirement between you and something else, you can use it as a buffer. And it's an attractive feature for a potential home buyer. So we can do everything on site and use the total system, and you don't have to go searching for water. And especially in places like Arizona, we're looking at one in Arizona right now. So we can reuse 100% of that water. Zero liquid.
So you mentioned the capital cost. The cost of building this Powell Water microalgae system will be less than building a sewer line, 500 miles to the next city to take care of it. I mean, so the hookup fees and that sort of thing, you're going to spend the money somewhere, but if you put it in your own Powell Water microalgae system, you keep that resource in your community, you save your water.
Well, it's so interesting. I'm actually give you a real application that I've worked on is I'm doing a 70 lot subdivision, but the sewer line has to be extended. I'm sorry, it's 300 lots or 70. And so if you go with a septic field, it goes all the way down to 70 lots because you've got to meet either 1 acre, half acre, depends where you are, requirement. It could be 2 acres. And it was something shocking to extend the sewer line 2 miles with a lift station and everything was something like $2.5–3 million. And you can't, it's
We'll build you a system for that, and you'll make it look like all park and golf course.
okay. I might hold you to that.
Well, we hope so.
But that's the flexibility. That's the flexibility and the creativity that this technology brings to almost any application. You can fit it in any existing lagoon anywhere. Like Round Mountain, we've got 6 lagoons we're going to use that are existing, and we can fit in that. So, yeah, very flexible.
You mentioned that. I'm just thinking from like a civil engineering, like a subdivision kind of thing. Usually you have a detention pond or something to offset your stormwater that you create. And that counts towards that open space, right? That's what they'll do. And then if you add yours into that as well, I bet, I'm not 100%, I bet you're getting close to that 15% that they're looking for.
Yeah,
so that retention pond that you're talking about, in a lagoon, it's just the space above the top of the lagoon. So the space is there, it's just a little deeper. So when the rain's coming, it surges a little bit. It just fills up, and you got a 21-day retention in your lagoon, so it fills up a little bit, and then you actually have treated water to discharge. You save your water, so it all works out well.
Do you have applications where they'll let you take the stormwater into your lagoons?
yes.
Absolutely.
I've never heard of it, so that's why I'm asking.
If you have city water on your streets, if you have a gutter or that goes into your sewer system, that's going into your lagoons. It's just sort of hidden on the way, but it goes right into your sewer plant. It flows through the system.
All of the sewer systems back east in the early days were combined stormwater wastewater systems. Caused lots of problems, and they're now working very hard to separate those systems. And if I don't have to combine them, I don't. I like to keep them separate because we like to keep the sewage flow. We like to keep as high strength sewage in there as we possibly can.
Okay.
Beautiful for storm sewer or stormwater.
Understood.
Yeah.
Wow. I feel like I just got a short course in what y'all do. This was super, super educational. Where do people find you if they're trying to reach out to you, learn more about your system?
You can go to our website, www.powellwater.com. Judd Sundine answers his phone all the time. You can call Judd on the phone. We like to be accessible, absolutely.
Okay.
Or they can call you, and you can send them to us.
I'll send them their contact for sure.
Or,
okay.
you could contact Colorado Rural Water Association. They come around and visit all the time. And you could ask them, is there any way that you could help our lagoons to get in compliance and meet the 2027 regulations that'll come? And they can feed that back to us. So there's lots of ways for people to find us. Judge, you want to tell them when the Colorado Rural Water Association meeting is this year?
Yeah, that's coming up in March, or let's see, what date is that for sure?
First week in April.
First week in April. Yeah, 6th through the 9th. And that's up in your neck of the woods, Jeff.
Loveland at the event center.
Loveland at the event center.
Ranch complex. What we do there for the small town guys, because it's part of their training too, so most of them go and get their points there. We actually run pollutant or paint through an electric coagulation system bench test, and we'll probably run 5 tests a day. And when the people see the water that comes out of that and the paint we put in it to begin with, and they see the end result, it's just they go muttering down the aisle. They just can't. It takes a day or two to get your head around it. It's so complete.
We'll make sure you get a good filming of that and post that on right there on your landing page on your website, because that would be pretty neat just for the average person to come across.
Yep.
And we would like to invite you to come and take that picture, because you would do a much better job at that than any of us. So please come and see us at the Colorado Rural Water Association.
All right, sweet. I think that wraps it up for today. Next week, we've got a really interesting guest. Taylor Pearson works over at Glacier Construction, and he's a third-generation construction professional, and he is really redefining the expectations and what we would want out of our contractors. All right, guys, thank you so much for being on today, and we'll see you all in the next one.
Good to meet you.
Thank you very much.
Thank you.
Goodbye.